On a dark, moonless night, a misty light reaches up across the sparkling vault of the heavens. At first, it looks like a cloud or a puff of smoke that could blow away on a stiff breeze, but it holds to its place among the stars. Because this is something more permanent and more intriguing than a passing cloud. This is what the Romans once called the Via Lactea, the Milky Way. And for astronomers through the ages, it has proved to be a pathway to discovery. To ancient skywatchers, the Milky Way was a mystery that became a myth. Some saw it as the wake of a celestial ship, others as the seam where the two halves of the sky were stitched together. But these stories and legends say more about the people who told them than they do about the true nature of the Milky Way. To the ancient Greeks, the Milky Way was formed when the goddess Hera awoke to find a strange infant, the baby Hercules, suckling at her breast. The divine milk bestowed immortality, but when Hera realized she'd been tricked, she pushed the babe away, and the spurting milk sprayed across the sky. Today, our word galaxy comes from the Greek word for milk. But stories aside, the Milky Way's true nature was hidden until people could see it through a telescope. It was 1609 when Galileo first turned the new invention toward the Milky Way's misty light and recorded what he saw. Galileo had discovered that the Milky Way is made up of countless stars, stars that are too far and too faint to see individually. Yet together, they paint the sky with a luminous glow. It was a realization that changed everything because it gave depth to the night sky. And it meant astronomers were free to explore a heavenly realm that the ancients had never dreamed of. Galileo noticed that the stars in the Milky Way are sometimes grouped in clusters. And as telescopes improved, astronomers discovered something else. Clouds of glowing gases called nebulae that would later prove to be the birthplaces of stars. Many of them located along the Milky Way, like gems on a cosmic necklace. But even as the telescope uncovered the hidden treasures nestled within the Milky Way, it left a big question unanswered. Why is the Milky Way confined to a narrow band that wraps around the sky? It would take another century and a half after Galileo before someone had the beginnings of an answer. In 1785, William Herschel, a German-born musician and astronomer working in England, was already famous for his discovery of Uranus. It was the first planet in the solar system to be spotted with a telescope. Now Herschel was ready to turn his attention to the placement of the stars around the sky, including the Milky Way. His strategy was straightforward but painstaking. Pointing his telescope at over 600 different locations, Herschel proceeded to count all the stars he saw in each region, and he estimated the relative brightness of each star. Herschel guessed that fainter stars were further away than brighter stars. So when he put it all together, he came up with a picture of the universe that looked like this. It shows that we are embedded in a vast system of stars that has a flattened shape, like a giant millstone or a disk. In some directions, the stars are relatively few in number, but along the midplane of the disk, the stars become more numerous, their light adding up to form the glowing band of the Milky Way. Herschel's map was a huge step forward, but it was also just the tip of the cosmic iceberg. For beyond the limits of Herschel's telescope, a far grander Milky Way was still waiting to be discovered. By building on the work of William Herschel, astronomers in the 19th century had verified that our solar system is located within a galaxy of stars, shaped like a giant disk. This explains why the Milky Way appears to us as a glowing band of light stretching across the sky. When we look along the band, we're looking into the disk. But astronomers were not entirely satisfied with this early picture of our galaxy. For one thing, it meant the solar system had to be located near the center of the Milky Way, an unlikely coincidence. And without a way to measure the true distances to the stars, there was no way of knowing how accurate this picture of the galaxy might be. To get a deeper understanding of the Milky Way, astronomers needed new tools and new ideas. By 1912, they had both. The new idea was a way to directly measure distance in deep space, and its discovery was entirely unexpected. In the era before electronics, Henrietta Leavitt was one of several women employed by the Harvard College Observatory to do mathematical calculations. At that time, large amounts of data were flooding into the observatory, thanks to the development of astronomical photography. The female computers who worked at Harvard were not expected to make scientific discoveries of their own. But that is precisely what happened when Leavitt noticed a pattern in a certain type of variable star called a Cepheid variable. Leavitt saw that each Cepheid pulsed with a regular cycle, and that the length of the cycle was related to the total amount of light coming from the star. Simply by timing the pulsations of a Cepheid variable, astronomers could now calculate the star's true brightness, and then work out its distance by comparing that to how bright it appeared in the sky. The method was quickly put to use with the help of astronomy's most powerful telescope of the time, the 60-inch reflector high atop Mount Wilson near Los Angeles. Backed by the telescope's unprecedented power, Harlow Shapley, a crime reporter turned professional astronomer, would make galactic history. Shapley used the giant scope to examine globular clusters, distant concentrations of stars with a distinctly spherical shape. Each globular cluster contains hundreds of thousands or even millions of stars, circling around one another like bees in a swarm. Shapley believed that these clusters, in turn, must circle around the gravitational center of the Milky Way. By using Cepheid variables to measure the distances to the clusters, Shapley was able to work out the location of a point in space around which all the clusters appeared to be concentrated. The result changed everything. It showed that the real center of the Milky Way is located tens of thousands of light years away from us, in the direction of the constellation Sagittarius. For astronomers, the revelation was a cosmic wake-up call. Centuries earlier, it was Nicholas Copernicus who had nudged Earth out of the center of the solar system and put the sun there instead. Now it was Shapley's turn to push the solar system away from the center of the Milky Way. Shapley's discovery relegated us to the suburbs of a galaxy that is much larger than anyone had previously imagined. Today, astronomers estimate the Milky Way is more than 100,000 light years across. Yet even in Shapley's time, there was growing evidence that this vastly expanded Milky Way was only a small piece of a far grander cosmic reality. That evidence came in the form of a class of faint, fuzzy objects scattered around the sky that were coming into focus as telescopes improved. Many looked like little spindles. Others had a distinctly spiral shape. To some, it seemed that these faint swirls must be newborn solar systems forming within the Milky Way. But there was also a more radical possibility. Could they instead be other galaxies, like the Milky Way, but located far off in the cosmic distance? In the early 1920s, astronomer Edwin Hubble was able to prove that the answer was yes. Using the newly built 100-inch telescope at Mount Wilson, Hubble zoomed in on the largest of the mysterious spirals, the Great Nebula in Andromeda. There, he spotted Cepheid variables, the pulsating stars that would again prove crucial. This time, they allowed Hubble to calculate the true distance to Andromeda. The results would become a turning point in our understanding of the cosmos. Hubble's measurement showed that Andromeda must be a separate galaxy, far beyond the borders of the Milky Way. Today, astronomers have pegged its distance at more than 2 million light years away. Other galaxies are millions, even billions of light years farther. Hubble had discovered the rest of the universe. But he had also given astronomers a new way to think about the Milky Way by comparing it to other galaxies. The era of galactic exploration was about to begin. By the mid-1920s, astronomers had realized that the universe is full of galaxies. Like islands in a cosmic sea, the galaxies are separate systems, each containing hundreds of billions of stars. But this revelation raised many new questions about our own galaxy, the Milky Way. Was it a spiral system, like some of the others, that could be seen from afar? And if so, how would we know? It had taken centuries for astronomers to figure out that the Milky Way is shaped like a large disk, with the solar system located about 2/3 of the way from the center. Now the challenge was to map the Milky Way from the inside. This was no easy feat, and a big part of the problem is dust. Even ancient astronomers could see the Milky Way does not have a uniform appearance across the sky. Instead, it looks patchy and uneven, In some places, it seems split by dark rifts. This is because the Milky Way is interwoven with vast clouds of interstellar dust that block much of the galaxy from our view. Yet despite this visual barrier, there are clues that helped astronomers discern our galaxy's true shape. Among the first to follow those clues was American astronomer William Morgan. In 1951, Morgan was working at the Yerkes Observatory northwest of Chicago, where he was studying blue supergiant stars, the hottest, brightest stars in the galaxy. One night, while looking in the direction of the constellation Perseus, Morgan realized that a number of the giant stars he had been studying in that part of the sky were all located at about the same distance, between 5,000 and 8,000 light years away. And so too is the Perseus double star cluster, a well-known feature in the same part of the sky. Morgan realized that the double cluster and the giant stars together traced a line through space, as though marking a structure embedded within the Milky Way. He had discovered the Perseus arm, one of the great spiral arms of our galaxy. Before long, other familiar sites scattered along the Milky Way were also shown to be part of the Perseus arm. Among them is the spectacular Crab Nebula, the remnant of a supernova explosion that was recorded in 1054. But if there was one spiral arm, there should also be others. By looking in the opposite direction from Perseus, astronomers found they could see traces of another arm that is located closer to the center of the galaxy. This is the Sagittarius arm, home to a dazzling array of star clusters and nebulae that adorn the southern Milky Way. Spectacular sights, like the Trifid Nebula, make this part of the sky a visual paradise. Closer to home, astronomers have determined that our own solar system is part of the Orion Arm, a smaller structure that may be no more than a spur branching off of Sagittarius. Yet the Orion Arm, too, is loaded with amazing sights, which loom large in our view because they are relatively close by. It is when we look down the length of the Orion Arm that we see the nearest, and to us, the most spectacular star-forming region in the sky. The Great Nebula in Orion, where thousands of new stars are being born before our eyes. Aided by radio telescopes and infrared satellites that can see through the galaxy's obscuring dust, astronomers have now peered deeply into the Milky Way to map its structure in detail. They have detected more arms and also confirmed that the Milky Way is not just a spiral galaxy, but a barred spiral. Barred spiral galaxies are common in the universe. Their elegant appearance is the product of an evolutionary process that causes material within the galaxy to form a horizontal bar running across the center. Now, more than 60 years after Morgan's initial discovery of the Perseus Arm, astronomers can show us what the Milky Way might look like if we could view it from the outside. This is the result. An artist's view that shows our galaxy as a barred spiral with two prominent arms. One of them is the Perseus Arm, the first to be mapped. On the opposite side is the Scutum Centaurus Arm. It's much harder to make out from Earth, but astronomers have found that it hosts massive clusters of hot young stars, like this one, imaged in infrared light by the Spitzer Space Telescope. Completing the view are the lesser spiral arms that wind their way between the two larger ones, including the arm where our own solar system is located, right here. This is a view that no telescope can show us, but one that is supported by years of observation across the entire Milky Way. The mapping of our galaxy is one of astronomy's great achievements, but it's more than just a map. It's a snapshot of a dynamic star system with a history that has unfolded over billions of years, a history that relates directly to our own existence. In that sense, the spiral may be the ultimate cosmic symbol of life, for it's in spiral galaxies that new stars and new planets are born. It's the same process that led to our own solar system's creation in the Milky Way. In that sense, the spiral may be the ultimate cosmic symbol of life. For it's in spiral galaxies that new stars and new planets are born. And sometimes civilizations like ours, with a desire to map and to explore the universe around them. In all of human experience, there are few sights as inspiring as a dark sky full of stars. Throughout history, our nightly view of the universe has fueled our collective imagination. It has helped give birth to great art and deep insights. But when it comes to the birth of the universe, not even the most creative work of imagination can rival the story that science has now revealed. It's a story that starts with a bang. Welcome to the Big Bang, the energetic outburst at the start of cosmic history that triggered the expansion of space and the creation of all matter. This is our ultimate beginning. The discovery that there was such a beginning is one of the signature triumphs of 20th century science. Now, the challenge to understand it is underway. Every great civilization in history has its creation story, the explanation that answers the question, how did all of this get here? In some ways, the Big Bang Theory has a lot in common with those stories because, like them, it conjures up a vision of supreme forces and astonishing events beyond human experience. The difference is that the Big Bang story is backed up by evidence, evidence that we can find all around us if we know how to look. This is Europe's Planck satellite. Launched in 2009, it's an orbiting time traveler that has reached back across more than 13.5 billion years to bring us to the threshold of the Big Bang. Planck has given us the most comprehensive view to date of a crucial turning point when light was first able to move freely through space and carry with it information about how the universe began. To achieve this view, Planck has probed deep into space in every direction, creating a map of the entire sky. But what that map shows is not a familiar scene of stars and galaxies. Rather, it's the faint signal that emanates from the darkness beyond, the cosmic background that lies behind everything else. This is a direct view of the universe when it was only 380,000 years old, just a tiny fraction of its current age. On the face of it, such a view might well seem impossible because it suggests that we can witness something that took place before Earth even existed. But in fact, we can, thanks to the finite speed of light. Light is the fastest thing we know in nature. It travels through space at nearly 300,000 kilometers per second. At that speed, the light we see from the moon takes just 1.3 seconds to reach Earth. That's incredibly fast, but it still means that when we look up at the moon, we are looking into the past, a past that took place on the lunar surface 1.3 seconds ago. The planet Saturn is much farther than the moon, so its light takes longer to reach us. When we gaze at Saturn's rings through a telescope, we are also gazing more than 1 hour back in time. Looking beyond our solar system, the difference between past and present becomes truly dramatic. Here are the Pleiades, a brilliant cluster of stars located some 400 light-years away. That means when we see the Pleiades, we see them not as they are now, but as they once were, 400 years ago, around the time Galileo was recording his first view of the Pleiades through a telescope. But our ability to time travel becomes truly impressive once we peer beyond the boundaries of our own Milky Way galaxy. Here is the Andromeda Galaxy, the most distant object visible to the naked eye. It lies more than 2.5 million light-years away, so our view of Andromeda actually shows what this galaxy looked like 2.5 million years ago. That's long before the first Homo sapiens walked on Earth. Such a span of time is incomprehensible on a human scale. On a cosmic scale, it's a short step. Probing deeper into space with powerful telescopes, we see countless galaxies that are tens or hundreds of millions of light-years away. Today, as we push to the farthest extremes of visibility, we can just make out the light from galaxies that are 12 billion light-years away. Seeing them means we can see more than 90% of the way back to the Big Bang. Beyond this point, there are no more galaxies to observe, because at such a remote and early time, galaxies hadn't formed yet. But we can still look farther, to a time when light came not from stars or galaxies, but from the glowing fog of hot gas that filled the universe in the aftermath of the Big Bang. This is where the Planck satellite has taken us. And it's here that we can find the clues that will lead us to a deeper understanding of the Big Bang. $13.5 billion years ago, our universe looked very different than it does today. This is a time just a few 100,000 years after the Big Bang, when space was filled with particles still too energetic to form atoms. Today, that early stage in cosmic history is imprinted in the heavens, revealed in this detailed map from the Planck satellite. To the eye, the map seems to lack an apparent pattern. But when analyzed mathematically, these colored speckles provide a detailed measurement of the basic properties of the universe and a window onto the Big Bang itself. The key to understanding the map is to realize that it's a record of temperature. It's showing us a universe in the process of cooling down from its white-hot infancy. Red represents distant regions of space that were slightly warmer than average in the remote past, while blue is for those regions that were slightly colder. These differences are like cosmic seeds that allowed matter to accumulate in some pockets of space while leaving others mostly empty. Today, the vast clusters of galaxies we see all around us are the byproducts of this primordial clumping of matter. But if Planck can look back to a time when all of space was filled with a white-hot gas, then why doesn't the sky look white now? The answer to that question challenges one of our deepest intuitions about the universe: the idea that it's always been here. In ancient times, looking into the heavens was like coming face to face with eternity. Perhaps that's because here on Earth, time brings growth and decay. While up above, the stars appear timeless. Aristotle, the most influential of the ancient thinkers, thought he had proved the universe was eternal. For him, the notion that there could be nothing before there was something offended reason itself. But when Isaac Newton discovered his law of gravity, a problem with eternity soon emerged. Because of gravity, the stars must all be attracted to one another. Yet if the universe is eternal, why haven't the stars already converged in one place? That question lingered uncomfortably for more than 2 centuries, right up to the 1920s. By then, there was a new theory of gravity, thanks to Albert Einstein. And astronomers had realized that stars are grouped into galaxies, and that galaxies are scattered through space. But the problem of eternity remained. Over an endless span of time, gravity should have drawn all the galaxies together. To avoid this contradiction, Einstein changed his equations in a way that would exactly counterbalance the influence of gravity across space. But Einstein soon found out that he needn't have bothered. In 1929, following up on earlier work by other astronomers, Edwin Hubble announced that most of the galaxies are moving away from our own. He discovered this by spreading out the light of each galaxy into a spectrum, like a rainbow. anything that is moving away will appear to emit light that is shifted toward the red end of the spectrum. That's exactly what Hubble saw, and the farther away a galaxy was located, the faster it seemed to be retreating. For Hubble, and for scientists since then, the most logical explanation is that space itself is expanding and pulling the galaxies along with it. On a human scale, the expansion of the universe is happening too slowly for us to notice. It amounts to every meter of space growing by just the diameter of a single atom every 10 years. That's not enough to overcome the gravity that holds stars together. So the Milky Way isn't getting any bigger, and neither are we. But in the great void between the galaxies, the expansion of space is adding up. And it means that overall, the galaxies are quickly flying apart. It also means that if we journey back in time, then the galaxies we observe today were once much closer together than they are now. And at some point in the past, there would have been no distinct stars or galaxies at all, just a continuous blaze of hot matter. This is the universe as seen by the Planck satellite. But today, space has expanded so much that the light from this early period has been redshifted beyond the range of the human eye, past the infrared, to ultimately become a signal in the microwave part of the spectrum. That signal was discovered by accident in 1964, when Robert Wilson and Arno Penzias, two radio astronomers from Bell Labs, turned an antenna toward the heavens and couldn't understand why the entire sky was giving off microwaves. Without realizing it, they had discovered the cosmic background, proof that the universe as we know it is not eternal, but had a definite beginning in time. A Big Bang. But there was more to come. As the space age blossomed, so too did the realization that this message from the distant past held the key to our cosmic origins. The Big Bang Theory tells us the universe that we see today was born out of a white-hot mixture of particles that would eventually cool down to make atoms, stars, and galaxies. But because the universe is expanding, that brilliant beginning has faded from view. Luckily, it can still be found in the form of a cosmic background of microwave energy coming from every direction in space. And space is the best place to see it. In 1989, NASA launched COBE, the Cosmic Background Explorer. Its mission was not just to detect the cosmic background, but to see whether it might reveal important details about how the universe evolved. The task was not an easy one. Previous studies with high-altitude aircraft had already shown that the cosmic background is remarkably uniform across the sky. Yet somehow, that uniform glow from the distant past had given way to the very diverse universe we live in now. A universe containing great congregations of galaxies, surrounded by enormous voids of empty space. So, as COBE began to map the entire cosmic background, scientists searched for subtle differences hidden in the smoothness of the ancient universe. What they discovered was a remarkable confirmation of the Big Bang. In this Kobe image, the cosmic background appears blotchy, showing very slight differences in temperature on the order of 1/100,000th of a degree. Scientists were ecstatic. Although these variations were minuscule, they meant that Kobe was seeing the earliest hints of large-scale structure in the universe. It also meant that the cosmic background could serve as a link to an even more distant past. Scientists realized the blotches were the traces of momentary fluctuations in energy that occurred when the universe was just a fraction of a second old. But as space rapidly expanded, those tiny fluctuations were stretched to giant size, eventually leaving their mark on the cosmic microwave background. Kobe had revealed the power of the cosmic background as a window into the Big Bang. Now scientists were eager to learn more. Following the success of Kobe, NASA began work on the Wilkinson Microwave Anisotropy Probe, WMAP for short, which was launched in June of 2001. Like Kobe, WMAP was designed to image the entire cosmic background, but it would do so in much greater detail. The stunning result would put to the test theories about how the Big Bang unfolded. For one thing, WMAP confirmed that much of the mass of the universe is in the form of invisible dark matter, consisting of undiscovered particles that are heavier than those that make up stars and galaxies. WMAP brought us a huge step closer toward understanding the Big Bang. But the Planck mission would go even further. Planck was built to survey the cosmic background at more wavelengths and at even higher precision than WMAP. After more than 15 months of scanning, scientists began carefully peeling back the layers in Planck's ultra-sensitive view. First, sources of microwaves that are close by in space had to be subtracted from the image. Next, scientists stripped away all the energy coming from distant sources within the plane of the Milky Way, and from the wispy dust clouds that are pervasive throughout our galaxy. Finally, what remained was the cosmic background itself, seen as never before. The result was a triumph. When it was released in March of 2013, it was clear the new map offered a remarkable portrait of the universe in hard numbers. Among those numbers is the precise age of the universe, which Planck measures at 13.819 billion years old. Planck also provided a detailed breakdown of how the contents of the universe are divided between ordinary matter, including stars and galaxies, dark matter, which gives off no light but accounts for most of the mass in the universe, and a third ingredient called dark energy, which is causing the expansion of space to speed up over time. Such numbers are crucial because they can help cosmologists distinguish between different variants of the Big Bang theory. Today, the dominant idea about how the universe came to be is called inflation. It proposes that in the first trillionth of a second after the Big Bang, the universe expanded exponentially, driven by a release of energy from the vacuum of space. Among other things, inflation explains why the universe looks so similar across great distances in every direction. Scientists working with Planck say that it rules out some versions of inflation, but is consistent with others. However, there are also alternative ideas, including some that say the universe we know today is part of a repeating cosmic cycle. If so, there may have been other universes before this one. To help distinguish between these possibilities, scientists are now searching for signs that gravitational waves produced by the Big Bang left their mark on the cosmic background. Meanwhile, perhaps the most important result from the Planck mission is that across many scales, the cosmic background looks mathematically simple. This in itself may be telling us something deeply profound about the cosmos, a universe that began with a bang, but that has evolved into a symphony of forms and phenomena. A universe that may have started simple, but that has become a truly inspiring place. At a distance of 150 million kilometers from Earth, the Sun is all the star we need. Its energy churns our atmosphere, keeps our oceans liquid, and makes life possible. But imagine if the Sun were more than 3 times larger in our sky and blasting every exposed surface with up to 10 times as much energy. Then Earth would be a very different world, a world ruled by heat and light. A world like Mercury. With its baked and battered surface, Mercury seems like a no-man's land among the planets. But it's a no-man's land that scientists need to explore. As the nearest planet to the Sun, Mercury lives in a cosmic hot zone that holds important clues to the origins of our solar system. And it may be our key to understanding conditions on countless alien worlds scattered throughout the galaxy. For centuries, Mercury eluded astronomers' best efforts to learn its secrets. The reason comes down to geometry. As seen from Earth, the angle between Mercury and the Sun is never more than about 30 degrees. The only way to separate the planet from the Sun's overpowering glare is to look very low toward the horizon immediately after sunset or just before sunrise. Under such conditions, even the largest optical telescopes in the world were not able to show any detail on Mercury's surface, right up until the dawn of the space age. All of that changed with Mariner 10. Launched in 1973, this intrepid spacecraft was designed to fly by Venus. But scientists realized they could get 2 planets for the price of 1 by including Mercury as a second target. During 1974 and 1975, Mariner 10 made 3 separate passes of Mercury, coming to within 327 kilometers of the planet's surface during its 3rd and final approach. During those historic encounters, centuries of speculation were replaced with a stark new picture of the solar system's innermost world. Mariner 10 revealed a heavily cratered planet that looked a lot like Earth's moon. Most of the craters date back billions of years. Because Mercury is too small and too hot to hold on to a thick atmosphere, its surface does not experience erosion from water or wind. Yet hidden in this ancient surface are tantalizing signs that Mercury has changed over the eons, and that despite its outward appearance, Mercury is very different from our moon on the inside. One clue is the planet's surprisingly large mass. Mariner 10 found that Mercury is nearly 5 times more massive than the moon, even though its diameter is only 40% greater. To be so heavy, Mercury must conceal a huge metallic core, covered by a relatively thin skin of lighter rock. This idea was further reinforced by Mariner 10's discovery that Mercury has a magnetic field. Although it is much weaker than Earth's, the presence of the field suggests that at least part of Mercury's core is still in a molten state. Mariner 10 tried to glean further clues from its reconnaissance of Mercury, but during its 3 brief passes, the spacecraft imaged less than half of the planet's surface, and what it found left many unanswered questions. Clearly, another mission to Mercury was needed, one designed for a much longer stay. But even though Mercury beckoned, the dream of returning would remain unfulfilled for nearly 30 years. At last, on August 3, 2004, NASA's Messenger spacecraft set out to become the first planetary probe to orbit Mercury and reveal its features and characteristics in detail. But just getting there would be half the challenge. Mercury is much closer to Earth than most of the other planets in our solar system, but it also sits deep within the Sun's gravitational field, which causes it to travel through space at a drastically different speed, roughly 65,000 kilometers per hour faster than Earth. In order to put itself in orbit around Mercury, rather than just sail by, Messenger would first have to match its speed to the planet's. Paradoxically, that meant the spacecraft would have to lose energy to allow it to gradually spiral in closer to the Sun. The journey would take over 6.5 years. Along the way, Messenger passed near to Mercury on 3 separate occasions, giving scientists a chance to test the probe's cameras and sensors. The results were spectacular, but the fleeting glimpses only whet scientists' appetite for more data. Finally, in March 2011, Messenger approached Mercury for a 4th and final time, this time moving at just the right speed to be captured by the planet's gravitational pull. The long-awaited exploration of the solar system's innermost planet was set to begin. Thanks to Messenger, Mercury was finally getting its moment in the Sun. Elusive and fast-moving in the twilight sky, the planet Mercury was named by ancient astronomers after the messenger of the gods. But not until 2011 would NASA's own Messenger mission be in a position to reveal one of the least explored worlds in the solar system. Messenger came well equipped for the job.
The sunlight at Mercury is so intense it would easily fry an unprotected spacecraft. So Messenger is covered in thermal insulation, and it carries a built-in system of radiators that are designed to draw heat away from its sensitive electronics. 2/3 of the surface area of its solar panels are mirrored to deflect rather than absorb solar energy and help control temperature. Finally, the main body of the spacecraft remains hidden from direct sunlight by a large sunshade made of ceramic cloth on a lightweight titanium frame. While the outer surface of the sunshade can reach 370 degrees Celsius, hot enough to melt lead, behind this essential barrier, the spacecraft operates at room temperature. Scientists expected the measures would be enough for Messenger to survive at least a year in the hostile environment around Mercury. But as Messenger began revealing the planet's complex geology, they were soon hoping for more. With both a wide and a narrow-angle camera, Messenger would be able to map the entire surface of Mercury down to features 1 kilometer across and zoom in on areas of special interest to see details as small as 20 meters across. The camera system could also be used to reveal slight color differences in Mercury's rocky terrain that would otherwise be too subtle for human eyes to discern. This would prove useful for reconstructing the multi-layered history exposed by Mercury's craters, and there were many craters to look at.
On the Moon, there's a long-standing tradition that craters are named after scientists and philosophers. On Mercury, it was decided instead that craters should be named after famous artists, composers, and authors. But while Mercury's craters may all have the arts in common, Messenger soon discovered some striking differences among them.
Here, Messenger zooms in on 2 craters, Degas and Bronte, located side by side. To the human eye, they seem identical in color, but Messenger reveals that Degas looks bluish relative to the brownish color of Bronte. This difference suggests that Mercury's surface includes layers of rock with different compositions. In this case, the impact has punched through a bluer colored rock underlying the brown. Elsewhere, the color differences are more complex, pointing to a rich and diverse geologic history that was not apparent to scientists before Messenger arrived. Sometimes, the effect of an asteroid or comet strike is obvious because it scatters material in bright rays across an older set of features. But not every part of Mercury's surface is shaped by an impact from above. In this intriguing image, a smudge of orange stands out against a darker colored landscape. Seen up close in black and white, the object at the center of the smudge looks like a tall peak inside a crater. But this is no ordinary crater. It's the likely scene of a volcanic eruption that sprayed out orange-colored material from deep within the planet's interior. Messenger has confirmed that Mercury is covered with features like this one that could only have resulted from volcanic activity. Here, a crater named Faulkner looks half-sunken into the landscape. The crater was probably flooded by lava, which topped its ancient rim and half-filled it with molten rock. Elsewhere, the large crater Rachmaninoff features a double rim, with the outer ring measuring more than 30 kilometers across. Color differences show that lava flooded the center of the crater long after it formed, and then spilled over into the region between the inner and outer ring. In other cases, the colors on Mercury's surface are harder to interpret. For example, some crater floors have bright hollows, which stand out against the darker rock and are completely unlike anything seen on the Moon. The exact nature of these bright patches remains a mystery, but scientists suspect they may be the result of some minerals becoming gaseous under the Sun's intense glare. One area where Mercury's color is especially revealing is the Caloris Basin. At 1,500 kilometers across, it is by far the largest impact feature on the planet. Caloris formed in the first billion years of the solar system's history, when a very large asteroid struck Mercury. Over time, other smaller craters scarred the basin. Then, lava covered the basin's vast central plain, leaving the raised rims of the smaller craters to stand out like blue islands. In contrast, the edge of the giant basin is marked with orange spots, where hot lava found a path to the surface through the shattered bedrock. Meanwhile, at the center of the Caloris Basin, MESSENGER has discovered a strange network of troughs that spread spider-like across the basin floor. These are indications that the surface of the basin may have been pulled or stretched in the past. With its oversized metallic core, there seems little doubt now that Mercury was once a geologically active planet, and that it remained so long after its formation. Now, aided by MESSENGER's trove of images and data, scientists are gaining a deeper understanding of the hidden forces that lie below Mercury's pockmarked surface. Hundreds of light years from Earth, a newly discovered world basks in the fierce light of an alien sun. This is one of scores of planets uncovered by NASA's Kepler mission, which was designed to hunt for worlds like Earth. Small, rocky, and at just the right distance from their stars to allow for the presence of liquid water. But in the course of its search, Kepler has also found many planets that are more like Mercury, orbiting much closer to their stars. Long neglected by planetary explorers, Mercury has now become our best reference point for understanding countless other hot worlds that populate our galaxy in the billions. And of special interest to scientists are those features on Mercury that are found nowhere else in the solar system. Features like towering cliffs that snake across Mercury's battered terrain for hundreds of kilometers. Here, one such cliff slices the ancient crater Rameau in half, leaving one side of the crater 2 full kilometers higher than the other. Having imaged the entire surface of Mercury, NASA's MESSENGER spacecraft has confirmed that cliffs like these are widespread around the planet. It's now believed that they formed when Mercury's giant metallic core cooled and gradually shrank. This left the planet with an outer skin that was too large. As the interior grew smaller, the surface buckled, forming cliffs like giant wrinkles in a planet-wide shrink wrap. The cliffs are an example of how Mercury's outer appearance has been shaped by internal forces. And as scientists combine MESSENGER data with ground-based radar measurements, the true nature of Mercury's dynamic interior is now coming into focus. A key discovery is that Mercury's metallic core is even larger than expected, accounting for 85% of the planet's total diameter. But while the inner portion of the core is likely made of solid iron, like Earth's, at least some portion of the outer core must be liquid. It is the motions within this electrically charged liquid that are responsible for generating Mercury's magnetic field. However, this picture presents scientists with a dilemma. If Mercury's core is made only of iron, it should have completely solidified by now. Since the smaller the planet, the more quickly internal heat escapes, even for a planet as hot as Mercury. This has led researchers to speculate that lighter elements, like silicon and sulfur, are present in Mercury's core in significant amounts. That would lower the core's melting point and leave the outer portion liquid. Mercury's liquid core may even be surrounded by a shell of solid iron sulfide, something not seen on any other planet. But while this explanation satisfies all the data, it leads to a larger mystery. In order to explain why Mercury's core is so large, scientists have speculated that Mercury was once more like Earth or Venus, a larger planet with a thick rocky mantle surrounding its core. Then, an enormous collision with another object blasted off much of that mantle, leaving the core intact. Another theory suggests that in the very early days of the solar system, the Sun went through a much hotter phase and boiled off some of Mercury's mantle with its intense heat. But the latest findings challenge both of these theories. Instead, it may be that Mercury formed as it is now, small but rich in lighter elements that were once thought not to have been abundant so close to the Sun. Whatever the explanation, it's clear there's something about Mercury's history and about the formation of the solar system as a whole that we don't yet understand. And that's not the only way that Mercury is defying expectations, because here, on a world so thoroughly baked by the Sun, Messenger has also discovered ice. As hard as this is to imagine, scientists already had hints that there was ice on Mercury, because radar observations indicated there is a highly reflective material somewhere near the planet's north and south poles. Mercury's poles are where we find deep craters whose bottoms remain in perpetual darkness as Mercury rotates on its axis. Shielded from direct sunlight, these craters are like cold traps for water vapor brought to Mercury by incoming comets that collide with the planet's surface. Although Messenger's cameras cannot see into these dark-bottomed craters, Messenger detected the presence of ice with a device called a neutron spectrometer, which measures how much the ice absorbs the energy of incoming cosmic rays. The data suggest there could be up to 1 trillion tons of ice on Mercury, to a depth of several meters. If so, the ice makes a tantalizing target for future explorations of the planet's surface.
Again and again, Mercury has proved to be an astonishing place. Not just a hotter version of our moon, but a fascinating world in its own right, with a history that is crucial to our understanding of rocky planets everywhere.
That is why the European and Japanese space agencies have now joined forces to send another mission to Mercury, which is scheduled to arrive early in the next decade. Once, Mercury was the least understood of planets. Today, it has become one of the most interesting, and the ambassador of a vast and emerging population of newfound worlds that together make up the cosmic hot zone. Far out in the Milky Way, a tiny particle of matter flies like a bullet through the vacuum of space. Propelled by colossal forces, the particle moves at nearly the speed of light, zipping by stars and the glowing clouds of gas where stars are born. Suddenly, a planet looms directly in front. Unstoppable, the high-energy particle rips into the planet's atmosphere. It collides with a nitrogen atom, destroying both the particle and the atom in a flash of pure energy. Now that energy creates new particles, which cascade downward, causing more collisions as they go. Soon, thousands, then millions of more particles spread out in a widening cone and then slam into the planet's surface. Earth has just been hit by a cosmic ray.
During the past century, astronomers have come up with a multitude of ways to get information from the universe. Stars give off visible light, but they also give off infrared, ultraviolet, X-rays, and other forms of light our eyes can't see. What makes cosmic rays so interesting is that they're not another form of light. They're bits of matter that are coming directly to us from deep space.
Cosmic rays carry information about powerful forces and events taking place thousands or even millions of light years away. But to understand what cosmic rays can tell us about the universe, we need to know how they are produced. In fact, it took a while for scientists to understand that cosmic rays even exist. The idea has its roots in the discovery of radioactivity by the French physicist Henri Becquerel in 1896. Radioactivity is the particle radiation that comes from atoms breaking apart spontaneously in the environment. When it was discovered, scientists realized that radioactivity might explain why they could never get an object to hold on to its static electric charge indefinitely. Because of radioactivity, in rocks and soil, there are always particles present near Earth's surface. Those particles can interact with anything that has an electric charge, causing that charge to gradually leak away. Over a century ago, scientists predicted this effect would disappear if they could take an electrically charged object away from Earth's natural radioactivity at the surface. The only question was how. The answer would come in 1911, when Victor Hess, a physicist from Austria, began a series of daring balloon flights that would eventually carry him and his instruments to a height of over 5 kilometers, roughly half the cruising altitude of a commercial jet airliner. As he ascended, Hess measured the presence of charged particle radiation like the kind produced by radioactive materials. At first, the radiation diminished with height, exactly as expected. But then there was a surprise. Starting around 1,500 meters, the situation reversed. Hess found there was more radiation than at sea level, and it was growing with altitude. By the time Hess landed, there was no longer any doubt. Earth was bathed in radiation coming from above, and a new field of science was born. Scientists eventually started calling the mysterious space radiation cosmic rays. By the 1930s, the invention of the Geiger counter had made it clear that cosmic rays were pummeling Earth at an astonishing rate, amounting to tens of thousands of incoming particles per square meter every second. Most of the particles were relatively low in energy, but some had enough energy to pass through rock, or even up to a meter of lead. Then, in 1938, the French physicist Pierre Auger took some Geiger counters high up into the Alps to measure cosmic rays there. He found that when two Geiger counters were set far apart, they sometimes recorded cosmic rays arriving at exactly the same time. Auger had discovered cosmic ray showers, bursts of particles that rain down in a widening spray, following the destruction of a single, much more energetic particle higher up in the atmosphere. Based on the size of those showers, some of the cosmic rays coming in from deep space were clearly more energetic than any particle produced on Earth. Now, scientists found themselves embarking on a new quest to understand where in the universe those energetic particles were coming from. Thousands of light years from Earth, a massive star ends its life in a brilliant explosion. This is a supernova, a stellar cataclysm that is one of the most energetic phenomena in nature. As the powerful shockwave expands, it creates a wreath of glowing gas, like this one, called Cassiopeia A, here revealed in striking detail by the Hubble Space Telescope. But could such an event also give rise to cosmic rays?
The riddle of cosmic rays is one that's being solved in stages. The ultimate goal remains understanding how these high-energy particles from beyond our solar system are created. But to get there, scientists first had to figure out what kind of particles they were.
For the most part, those particles never reach us here on the ground. Instead, they strike the atmosphere and unleash a torrent of secondary particles that shower down like so much subatomic shrapnel. By studying these secondary particles in the 1930s and 40s, scientists gradually narrowed in on the true nature of cosmic rays. What they found is that most cosmic rays, about 90% of them, must be single protons. Protons are positively charged particles that are part of every atom in the universe, but most of them occur in the form of hydrogen atoms. Atoms that are made of a single proton orbited by a single electron. Hydrogen is the most abundant element in nature. Stars are mostly composed of hydrogen, and so are the vast clouds of gas out of which new stars form. So whatever is making cosmic rays and sending them our way, it has plenty of raw material to work with. In 1947, a high-altitude balloon experiment revealed that most of the remaining 10% of cosmic rays are made of the nuclei of heavy atoms, like iron. Like protons, these atomic nuclei are stripped of their electrons, and they've been sent rocketing through space by a powerful force. But what? Even solar flares, the giant explosions that erupt from the surface of the sun, cannot account for the energies behind these heavier cosmic rays. But solar flares do offer us a hint about how cosmic rays are created. Because solar flares are caused by the release of magnetic energy. Under the right circumstances, a magnetic field can be used to accelerate an electrically charged particle, like a proton, to enormous speeds. Today, this principle is at work in the Large Hadron Collider, the world's largest particle accelerator, where huge superconducting magnets are used to send protons careening around a giant ring 27 kilometers in circumference. When the protons collide, the energy release is enormous, generating new particles that allow scientists used to explore the fundamental properties of matter. Amazingly, some of the highest energy cosmic rays are millions of times more energetic than the protons in the Large Hadron Collider. It means that somewhere out there in space, nature has created its own particle accelerators that would dwarf anything humans have built on Earth. But identifying them has proved a major challenge. Starting in the 1980s, an experiment called Fly's Eye in the remote Utah desert used sensitive detectors to spot the faint ultraviolet glow of cosmic ray air showers high up in the atmosphere. This allowed researchers to see what direction any particular cosmic ray was coming from in the sky. Yet, this did not help scientists figure out where cosmic rays ultimately come from. The reason is that the space between the stars is a complex network of magnetic fields that thread their way around our galaxy, and these fields have been bent and twisted by the turbulent motions of ionized interstellar gas. The magnetic fields completely scramble the directions of cosmic rays moving through the galaxy, so that from Earth's point of view, they appear to be coming from all over the sky, leaving no hint about where they originally came from. In their efforts to explain cosmic rays, scientists had run into a significant roadblock, one that would require them to search the heavens in a new and different way. This is our Milky Way galaxy, home to hundreds of billions of stars and vast clouds of dust and gas that stretch on for thousands of light years. It is a huge and complex system. And hidden somewhere within its depths are the sources of high-energy particles we call cosmic rays. As early as 1949, the nuclear physicist Enrico Fermi proposed the idea that cosmic rays are produced when protons and other charged particles are accelerated to high speeds by bouncing around within a changing magnetic field. But where in the galaxy might conditions make such bouncing around possible? Because cosmic ray particles are intensely energetic, the sources that create them must be able to somehow provide that energy. And those sources may also give themselves away by throwing off a high-energy form of light called X-rays. Here on Earth, X-rays from space are absorbed by our atmosphere, so X-ray telescopes must do their work orbiting high above Earth's surface. Today, the Chandra X-ray Observatory is our most discerning X-ray eye on the sky. Chandra has been used to peer into some of the hottest and most energetic regions of the galaxy, revealing views like this of the Carina Nebula, where interstellar gas is cooked to millions of degrees by newborn giant stars. This is a high-energy environment, but not one that has the kind of magnetic fields needed to accelerate cosmic ray particles. So instead of looking at places where stars are born, cosmic ray hunters have zeroed in on those places where giant stars have died violently. This spectacular ring is the remnant of a supernova, a vast stellar explosion that sprays matter outward in all directions, creating a rapidly expanding shockwave. The leading edge of this bubble can move at tens of thousands of kilometers per second, but that's still nowhere near the speed of a cosmic ray particle. However, scientists after Fermi realized that supernova shockwaves can compress and strengthen magnetic fields in the surrounding gas. Then, charged particles moving back and forth across the shockwave can pick up more and more energy through a process called Fermi acceleration. Eventually, the particles would be moving fast enough to break away from the shockwave and fly off into the galaxy. Here at last was a theory that could explain cosmic rays, but proving it would require another kind of space observatory. Fittingly, that observatory is NASA's Fermi Space Telescope. Named after Enrico Fermi, it has special detectors that can pick up gamma rays, a form of light even more energetic than X-rays.
5, 4, 3, engine
Launched
start.
in 2008, the Fermi telescope had been used to study the most extreme phenomena in the universe,
A gamma ray telescope searching for unseen physics in the stars.
like the supermassive black holes that lie at the centers of distant galaxies, or mysterious explosions known as gamma ray bursts. And Fermi has also turned its attention to two of the most interesting supernova remnants in the Milky Way. One is W44, a dramatic shell of expanding gas located 10,000 light-years away in the constellation Aquila the Eagle. The other is IC443, nicknamed the Jellyfish Nebula. It lies roughly 5,000 light-years away in the constellation Gemini. What these two colorful bubbles have in common is that they are both the result of supernova explosions expanding into dense clouds of interstellar gas. In theory, this should be the perfect situation for generating cosmic rays by Fermi acceleration. The Fermi spacecraft is the perfect tool for testing this idea. Its sensitive detectors can distinguish between gamma rays that are produced by different kinds of physical processes. But it would take more than 4 years of gathering data with Fermi for scientists to be sure. Finally, in February 2013, they were ready to reveal their results. What they had found was a clear signal, the first ever seen, of protons at high energies occasionally colliding to produce gamma rays. The type of signal exactly matched what was expected if the protons were being accelerated on their way to becoming cosmic rays. 100 years after cosmic rays were first discovered, the Fermi telescope had finally captured a glimpse of cosmic ray creation.
Scientists now know more about cosmic rays than ever before, but the search doesn't end here. Although they are rare, the highest energy cosmic rays are so powerful, even a supernova shockwave isn't enough to drive them. So now the search for new sources of cosmic rays is reaching beyond the boundaries of the Milky Way.
This is M87, a giant galaxy about 60 million light-years from our own. Deep in its core lies a black hole so huge its mass is equivalent to more than 6 billion suns. As it devours gas from the surrounding environment, the rapid spin of the black hole causes some of the gas to escape, forming a jet that extends hundreds of thousands of light-years into intergalactic space. The jet is wrapped in magnetic fields that may just be strong enough to create what are known as ultra-high energy cosmic rays. Because they are so rare, the experiments that hunt for these particles are huge, covering thousands of square kilometers in an effort to capture just a handful of the most energetic particles in nature. But if the theory proves correct, for the first time, these experiments may be able to prove that we are being hit by matter from another galaxy. Thanks to the discovery of cosmic rays, we know we have a direct connection to some of the most powerful phenomena in the universe. Now, as a new chapter of exploration opens before us, we are learning just how astonishing that link to the cosmos may prove to be. It's the summer of 1950, and at the U.S. government laboratory in Los Alamos, New Mexico, scientists are breaking for lunch. 5 years earlier, this was the home of the Manhattan Project, the top-secret effort to build the first atomic bomb. But now, in a lighter moment, the discussion at one table has turned to flying saucers. It begins with a humorous story involving aliens. But soon the scientists are debating when it might be possible to travel to the stars. Among those present is Enrico Fermi, a Nobel Prize-winning physicist whose many contributions included developing the world's first working nuclear reactor. After a while, the conversation turns to more earthly topics. Then, out of the blue, Fermi suddenly blurts out a question. Where is everybody? Fermi was still thinking about extraterrestrials, and he had just realized that something wasn't right. Fermi then did some quick calculations on the spot that confirmed his suspicions. If there were advanced extraterrestrial civilizations elsewhere in the galaxy, it's likely we would have picked up some sign of them by now. Maybe signs of several civilizations. The fact that it hasn't happened is now called the Fermi paradox, after the man who posed the question.
Fermi wasn't the first person to wonder why we haven't yet seen any signs of alien life in the universe. But as a gifted scientist, he framed the problem in a way that would resonate far beyond that lunchtime conversation.
Over 6 decades later, the Fermi paradox remains unsolved, even as the evidence has mounted that the basic ingredients for life, including carbon, oxygen, and nitrogen, are among the most common elements in the galaxy. Astronomers have also discovered hundreds of planets beyond our solar system and directly observed the swirling disks around young stars where new planets are forming right now. All of these new data continue to suggest that if life happened once, right here, it must have happened many times, increasing our chances of contacting an advanced civilization. This optimistic reasoning is further bolstered by the fact that life on Earth has a long history. We know from fossils that over the eons, many different kinds of creatures have called this world home, and that evolution has been very effective at ensuring that life continues to adapt and flourish with changing conditions. The earliest traces of life come not from fossils, but from microscopic patterns and chemical traces in ancient rocks. These show that bacteria were already living on our planet at least as early as 3.5 billion years ago. And that means the first cells and the first DNA must date back even earlier. Earth itself is no more than 4.6 billion years old. That's how long ago it formed, along with the other planets, out of the leftover debris that surrounded an infant sun. After allowing a few 100 million years for Earth's surface to cool and its atmosphere to stabilize, it seems that life must have appeared here almost as soon as it was possible to do so. The key ingredient was water. In liquid form, water is an ideal solvent, where molecules that are important to biology can interact and react. Because of the early and sustained presence of liquid water, life was able to gain a foothold on Earth. And it may be that Earth was not alone. In August 2012, NASA's Curiosity rover landed at Gale Crater on Mars. Over the next several months, as it meandered along the crater's dusty floor, Curiosity found convincing evidence that the rock beneath its wheels had formed in standing water. The presence of clay minerals in the rock suggests that the water was similar to fresh water on Earth and hospitable for life. That's a long way from showing that there once was life on Mars, but it does mean that for some period of time in the remote past, Mars was a livable planet, at least livable for microorganisms. Some suspect there could still be Martian life today, eking out an existence deep underground. So in our own solar system, it appears life arose in one or possibly both of the places where there was an environment that could sustain it. Even if Mars is a dead world, that's a 50% score. And in a galaxy filled with billions of planets, it's hard to imagine that life hasn't been equally successful out there among the stars. But as Fermi realized, there must be a hitch. Perhaps it was only a matter of looking for ET in the right way. By peering deep into the universe, astronomers have come face to face with the immensity of time. Observations of distant galaxies reveal that we live in an expanding universe. By measuring the rate of the expansion, cosmologists now estimate our universe began with an event called the Big Bang, which took place some 13.8 billion years ago. Our deepest views of the cosmos also reveal that by 500 million years after the Big Bang, the formation of stars and galaxies was well underway. If so, our own galaxy probably started forming about that time. In contrast, our solar system is less than 5 billion years old. It has been around for less than half the age of the Milky Way. This would seem to suggest that there has been plenty of time for other civilizations to arise within the Milky Way long before our own. So when it comes to finding someone else out there that we can talk to, time should be on our side. Instead, we have the Fermi paradox, the startling puzzle that asks, if life is so abundant on Earth, and if the galaxy has been around for such a long time, why have we not yet seen any sign of anyone out there? In 1950, Fermi's question was originally triggered by a conversation among physicists about traveling to the stars. But even if interstellar travel is impossible or impractical because of the great distances involved, the Fermi paradox still holds. That's because the technology already exists to probe the galaxy for radio signals from extraterrestrials. Around the time that Fermi asked his famous question, astronomers were already planning the construction of giant radio dishes to probe the heavens. For the first time in history, humanity had an ear on the cosmos. By 1960, American astronomer Frank Drake was using a 26-meter dish in Green Bank, West Virginia, to listen for any radio emissions that might be coming from alien civilizations. It was the beginning of SETI, the search for extraterrestrial intelligence. Drake was not expecting to hear a message specifically meant for us, but he knew Earth was sending out plenty of signals in the form of commercial broadcasts and military radar. A civilization even slightly more advanced than our own might be giving off far more. Right from the start, SETI presented a huge needle in the haystack problem. It was one thing to have the right sort of antenna for listening in on ET, but quite another to know where to point it and which of the billions of possible frequencies to listen to. Drake's approach was to point at a couple of the nearest stars that seemed similar to our Sun and to choose frequencies near 1420 megahertz, the frequency of radio waves emitted by hydrogen, the most common atom in the universe.
When Frank Drake began his search, enthusiasm for SETI was building. Since no one had looked before, it was possible that the skies would turn out to be flooded with signals from well-established civilizations, all talking to each other in a galactic social network. Maybe the answer to the Fermi paradox was simply a matter of switching on a radio receiver.
But that's not what happened. Drake's initial search came up empty. And so has every subsequent effort to pick up alien radio signals, at least so far. Among the most extensive was Project Phoenix, which used radio dishes in Australia and the United States to probe some 800 carefully chosen star systems. After the project wrapped up in 2004, scientists concluded that if an advanced civilization was using radio transmission to announce its presence anywhere within 200 light years of Earth, we would have discovered it by now. In comparison, the Milky Way is more than 100,000 light years across, so there's still plenty of galaxy left to search. But our ability to gather and sift through radio signals from space is rapidly growing more efficient, driven mainly by Moore's law, which projects a doubling in computer processing speed about every 18 months. In California, scientists at the SETI Institute are developing the Allen Telescope Array to vastly improve the speed and volume of radio-based searches. If technology continues to improve at its current rate, then by the middle of this century, humans will have listened in on more than 1 million star systems. If no alien civilization turns up by then, Fermi's paradox will be a more pressing problem than ever. and we'll be left to consider why the chemical and biological processes that led to our emergence has not been repeated elsewhere, or at least not often enough for us to find anyone out there to talk to. Our existence on Earth proves that life is possible in the universe. What it doesn't tell us is how probable life is. For 4 years, starting in 2009, NASA's Kepler spacecraft found evidence for thousands of planets in the small section of the sky where it trained its gaze. Although many of these finds still need to be confirmed with follow-up observations, the numbers suggest that across the Milky Way there are tens of billions of planets similar in size to Earth. But we also know there cannot be billions of civilizations out there trying to make contact with us, or we would have heard from some of them already. Where are they is the way Enrico Fermi once framed the question. Given the potential for so many civilizations in our galaxy, is it really plausible that we could be alone? Over the decades since Fermi posed his famous paradox, there have been many attempts to resolve it. One set of explanations explores the possibility that extraterrestrials exist, but that they either can't or won't communicate with us. For example, there may be intelligent life on other planets without advanced technology, or in an environment, perhaps underwater, where radio communication is not practical. We may also be overestimating the interest that alien civilizations may have in contacting us. As societies become more advanced, perhaps they also become more inward-looking. Some have suggested that aliens are well aware of us, but they're monitoring us quietly, like scientists studying another species in their natural setting. The trouble with all these speculations is that for every society we can imagine that doesn't want to say hello for some reason, we can also imagine others that do. For us, curiosity and communication have come with huge survival benefits. The more information we can gather about our environment, the better we can prepare for unknown threats or take advantage of resources that come our way. It stands to reason that at least some extraterrestrial civilizations must be curious and interested in communicating. We can even imagine that such a civilization would be sending probes out to the stars. In 2013, Voyager 1 became the first human-made probe to reach the edge of the solar system and cross into interstellar space. With a few centuries of improvements to our technology, we could be sending much faster and more sophisticated probes to the stars. These probes could be equipped with instructions for how to find a moon or asteroid with suitable resources for the probes to make copies of themselves that would be sent to explore further. The idea of a self-replicating machine was first suggested by the mathematician and computer science pioneer John von Neumann. If such machines could be built to travel through space at 1/40th the speed of light, about 400 times faster than Voyager 1, after a few million years, they would have visited every star system in the Milky Way. But that's just the blink of an eye in the lifetime of our planet. The fact that we have found no evidence for von Neumann machines in our solar system suggests that no one has ever built them, which in turn means that there can't be many advanced civilizations out there, or someone would have done it by now. This kind of reasoning has focused attention on the history of life on our world. and the remarkable chain of coincidences that has given our species virtual mastery over our entire planet. Perhaps we are more special than we think. Some have noted that even though life emerged quickly on Earth, complex multicellular life took billions of years to show up. If a planet can't maintain a stable environment for that long, then maybe the best it can manage is to be home to a world of bacteria. In 2000, astronomer Don Brownlee and paleontologist Peter Ward looked at how many things have to go right to have a planet like Earth. They concluded that while simple life may be very common throughout the universe, complex life is an exception. They called their idea the rare Earth hypothesis, and in the next decade or so, we may have a hint about whether they're right. Following on from the Kepler mission, scientists at the Massachusetts Institute of Technology are now developing the Transiting Exoplanet Survey Satellite, or TESS for short. Its goal will be to spot Earth-like planets crossing in front of nearby stars. If there is life on those planets, even microbial life, follow-up observations may detect traces of it just by analyzing the starlight passing through the planet's atmosphere. If TESS turns up planets that may be hospitable to bacteria, but nothing more, then we may indeed be living in a rare Earth kind of universe.
Of course, there is one more way of resolving the Fermi paradox, and that is to consider that the technology needed to make contact with another civilization may go hand in hand with the technology that would allow a civilization to self-destruct. So far, we've managed to avoid blowing ourselves up, but given the increasing pressure we're putting on our planet, it's fair to say our survival is far from guaranteed.
One of the great ironies of the Fermi paradox is that it came up in a conversation between brilliant scientists working in a military lab at the height of the Cold War. That should remind us that the paradox is not just a curious quirk of the cosmos, but an important caution for our entire civilization. If nothing else, Fermi's paradox tells us that long-lasting civilizations may be exceptionally rare, and that it will take great perseverance on our part if we are to become one of them. If we succeed, and then we do one day pick up a message from another intelligent species, we will have double reason to celebrate. It will mean that we're not alone, and that thanks to our careful self-preservation, neither are they. It's February 2013, and at Vandenberg Air Force Base in California, a lone rocket stands poised under a cloudless sky.
T-minus 10, 9.
As the countdown begins, there's tension in the air. It's a perfect day for going into space. But with so much riding on this one launch, there's good reason for mission controllers to be nervous. The Atlas V rocket carries an advanced space explorer, one with cameras that can peer in multiple wavelengths and reveal hidden details the human eye can't see. If this mission fails, decades of groundbreaking science will be in jeopardy. But if it succeeds, it will vastly strengthen our understanding of the most interesting planet in the solar system. The planet is Earth. And the mission is just the latest in a long line of spacecraft that have transformed the way we look at our home world. And that is precisely why there's so much at stake now. This mission, Landsat 8, is not just about launching another satellite, it's about preserving a data dynasty.
The Landsat program has already been running for more than 40 years, providing an unbroken record of our planet during a period of astonishing change. Now, with Landsat 8, researchers hope to extend that record for many years into the future. In the process, they may witness a transformation more profound than anything that was imagined when the Landsat program first began.
It was a beginning inspired by a very different goal. In the early 1960s, the Soviet Union was leading in the space race, and the United States was sparing no expense to overtake its rival superpower. The objective was to be the first to land a manned spacecraft on the moon. But along the way, the US first had to master the basics of getting its astronauts into orbit. The first flights were solo and brief. Astronauts had relatively little time to absorb the incredible views that they were getting as they looked down on Earth. But that began to change in 1962, at the tail end of the Mercury program. By then, US astronauts were equipped with high-quality handheld cameras, and they had the time to use them. The final Mercury mission lasted over 34 hours. The photographs that resulted were amazing, especially in an era when scientists were still using black and white aerial photos to study Earth's terrain. As the Mercury program transitioned into the Gemini program, the orbital flights got longer, sometimes lasting several days, and the pictures got even better. By 1966, Gemini astronauts had snapped about 1,100 images, training their cameras on mountains, lakes, deserts, and coastlines. Often their pictures brought into sharp focus remote regions of the Earth that were hard to access and poorly studied. These pictures were not only stunning, they were clearly useful for scientists. Before then, pictures taken from orbit had been used mainly to observe weather patterns. Now researchers were beginning to understand the benefits that might come from having a satellite dedicated to exploring Earth's surface from space. A leading proponent of the idea was William Pecora, director of the United States Geological Survey. Pecora could see that the space program had the potential to greatly improve our knowledge of Earth's agricultural and natural resources. And this was just when population growth and industrialization around the globe were making such information vitally important. So, in September 1966, Pecora pushed the US Department of the Interior to unveil a new program of space-based observation. Its centerpiece was called the Earth Resources Technology Satellite. But not everyone was enthusiastic about the idea. With NASA already deeply invested in a manned mission to the moon, government administrators were reluctant to spend still more money on another completely different space project. Others worried about the legal and political implications of launching a satellite that could see the territories of other nations up close from orbit. And then there was the US military, which had already been operating its own series of spy satellites since 1959. Defense officials were not at all eager for the public to grasp the remarkable power of surveillance from space. Despite these obstacles, the idea of an Earth-observing satellite for civilian use gradually gained support. In 1970, NASA got the green light to build such a spacecraft. Its design was a modified version of the weather satellites which had already been flying since 1964. But this spacecraft was equipped with cameras capable of imaging features on Earth's surface down to 80 meters in size, both in visible light and near-infrared. And it included a tape recorder for playing back data gathered from virtually any point on the globe. Assembly proceeded rapidly, and on July 23, 1972, the Earth Resources Technology satellite, ERTS-1, was successfully launched into orbit. Sadly, William Pecora, the geologist and federal administrator who had pushed so hard for the mission, had died in hospital just a few days earlier. He was 59. Pecora never had the chance to witness the scientific returns from the satellite, which was later renamed Landsat-1. But the returns were impressive. And over the next 5.5 years, Landsat-1 would provide a treasure trove of data about our planet. And it was not alone. In 1975, Landsat-2 was launched, adding to the program's reach and extending its lifespan another 5 years further into the future. That pattern would continue with a series of overlapping missions into the 80s and beyond. And not a moment too soon. Landsat may have been born out of the space race, but it would come of age just as scientists were racing to understand profound environmental changes taking place on Earth. Thanks to Landsat, they would have a front row seat. Off the coast of Labrador, a tiny speck of land less than 50 meters across pokes up above the frigid waters. Uncharted after centuries of maritime exploration, it was finally spotted by Landsat-1 in 1976. To this day, it's called Landsat Island. Since it began in 1972, the Landsat program has added countless details like this to our map of the world. Yet the real value of the Landsat program comes not from putting new places on the map, but in seeing what's on the map in an entirely new way. Every Landsat spacecraft is equipped to see Earth's surface in multiple wavelengths of light, including some that are beyond the range of normal human vision. By assigning different contrasting colors to these wavelengths, it's possible for researchers to bring out details that would be too subtle to spot in an ordinary color photo. Here, for example, a small but lush corner of Oman stands out in marked contrast to the barren desert that surrounds it. This region is different from the rest of the Arabian Peninsula because the mountains here capture monsoon rains during the summer, supplying water to a rich and fertile strip of coastal lowland. Elsewhere, this vividly colored section of Axel Heiberg Island in Canada's high Arctic shows the extent of icy glaciers, here seen in blue, among the island's rugged mountains, which appear in yellow. Landsat can also reveal other more ephemeral features. Here, newly transported river sediments form ghostly ribbons off the Mississippi Delta. While here, in the Pacific Ocean, about 600 kilometers west of Chile, wind blowing over a remote island forms a repeating pattern of eddies in the clouds.
There's no question that Landsat has given us a dramatically different perspective on Earth's natural geographic diversity. But even more revealing is the way the program has documented humanity's growing impact on the planet. Sometimes change operates at such a scale that we can only grasp its true impact by observing it from space.
Nowhere is this more true than the Aral Sea, once the fourth largest lake in the world, a vast inland sea that was the size of Ireland. Though it has existed for thousands of years, the Aral Sea has all but disappeared in just a few decades because the rivers that feed the Aral Sea have largely been diverted for irrigation. This succession of Landsat images captures the Aral Sea's disappearing act. As the waters shrink to oblivion, they take away a once thriving fishery and leave behind a barren, salty desert. Landsat has also proved crucial for documenting a very different kind of loss. In the Amazon basin, the program's satellites have witnessed the clearing away of vast swaths of rainforest for logging and agriculture. This sequence shows how that process has unfolded in Rondônia, a state in northwestern Brazil. The rainforest is first divided up in a fishbone pattern as logging roads extend into undisturbed territory. Then, the parceled sections of forest are systematically removed. Roughly 16% of the Amazon rainforest has disappeared since Landsat began imaging the region. Elsewhere, Landsat imagery has witnessed the ever-increasing scale of development around the planet. For example, the city of Las Vegas can be seen spreading rapidly across the Nevada desert, placing a major strain on water supplies in one of the driest regions of the United States. Meanwhile, halfway around the world, a new lake forms behind China's enormous Three Gorges Dam. Completed in 2012, this massive hydroelectric project displaced over 1 million people. Around the globe, the quest for energy and its consequences are a recurring theme, yielding some of Landsat's most arresting images. In the wilderness of northern Alberta, Landsat looks on as vast swaths of land along the Athabasca River are opened up for oil extraction. And along the Persian Gulf, the wealthy Emirate of Dubai, a product of the Middle East oil boom, shows off some geographic artistry by sprouting artificial islands in the shapes of palm trees and a map of the world. Yet it's clear that on the real world map, the continued use of oil and other fossil fuels is having a profound effect on the planet. Here, Landsat documents the startling retreat of the Columbia Glacier in Alaska. As global warming sets in, rapidly melting ice and rising sea levels seem to be the inevitable result. Yet, just as our awareness was growing about the magnitude of this change, Landsat's invaluable perspective on our planet was at risk of disappearing for good. As humanity comes to grips with global warming, the ability to continuously monitor Earth's surface from space has become the essential starting point for any future efforts to manage the planet's resources and preserve its priceless biodiversity. The Landsat program is tailor-made for this purpose. Because Landsat images are relatively wide-angle, they don't show details as fine as individual trees or buildings. Instead, Landsat offers a big picture view that is intended to capture changes on a regional scale. Each satellite in the series was designed to circle Earth in a polar orbit, allowing it to image the world in a series of strips from north to south. Starting with Landsat 3, each satellite was placed in an orbit that is just over 700 kilometers above Earth's surface. The orbit is also synchronized with the Sun, so that each time the satellite passes overhead during the day, the local time down below is about 10 o'clock in the morning. The timing and positioning of the orbit means a satellite can image any particular spot on the planet every 16 days, and always at the same time of day. This is especially useful for tracking long-term trends, because every time an image is captured of a particular location, the lighting angle is about the same as the time before. Because of this visual continuity, the Landsat database becomes more valuable the longer it accumulates, which is why researchers were especially worried when Landsat 6 failed during its launch in October 1993. The Landsat program had already narrowly escaped being shut down for budget reasons, and Landsat 5, though still running well, had already been in space for 9 years. It would have to hang on 6 years more before the US was ready to fund, build, and launch Landsat 7 in 1999. That launch was a success, but a few years later, the failure of a crucial piece of hardware meant the spacecraft was partially blinded and its images incomplete. It would be a long, hard battle to get the next Landsat approved. By the time it was ready for flight in 2013, Landsat 8 was not only the most sophisticated satellite in the series, it was also a rescue mission for the entire program. Then, just 6 weeks before the big launch, Landsat 5 finally gave out. After a record-breaking 28 years of observation, it stopped communicating with mission controllers in January of 2013. That meant only Landsat 7 was left, and it was no longer operating at full capacity. So, by February, with Landsat 8 on the launch pad, the fate of the entire program hung in the balance. Charging skyward on a column of white smoke, the rocket carried its precious cargo into orbit. A short time later, the good news was confirmed. Landsat 8 was successfully launched, and its systems were operating normally. Scientists were ecstatic and relieved. Over the coming weeks, the new mission would show off its prowess, sending back images even more spectacular than those of its predecessors. By May, the satellite was fully operational and returning more than 400 images per day. These first images from Landsat 8 make it clear that the entire program has now begun a new chapter, and that Landsat's continuous coverage will likely prove invaluable as we move into an unprecedented period of global change. By now, Landsat is not the only eye in the sky monitoring our planet. Every minute, we are circled by a range of Earth-observing satellites, like Terra, a multinational spacecraft operated by NASA that has specialized sensors for monitoring environmental change. Or like Canada's RadarSat program, a series of satellites that can see Earth both at day and night. Its radar vision penetrates clouds and fog to create dramatic, high-resolution images of the surface.
Looking at how things have evolved since the early days of Landsat, it's clear that we're now in a period of specialized planetary monitoring, one that no single satellite could manage alone. But Landsat, with its ever-growing record of our world, still provides an underlying foundation for an entire system of Earth observation.
Ultimately, that is where Landsat's greatest impact lies. In starting the program decades ago, researchers were not just creating a camera for photographing Earth from space. They were, in fact, creating a new field of science, the science of remote sensing. And as the pace of environmental change quickens around the globe, it's increasingly clear that this is one science we cannot do without.